We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Okay, my feet are out. Okay, I'm out. Really looks funny out there. See my glove out there, Jim.
Jimmy Moore, just not yet. Good morning, Gordo.
Yes, how are you?
How does it feel for the United States to be the new record holder?
At last, huh?
We're rolling up and we can't turn anything off. Finally increasing in a low roll.
We have a liftoff, 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed.
Hello and welcome. This is Michael Annis, and you are listening to episode 75 of the Space Rocket History Podcast. And now, Luna 10, Surveyor 1, and Lunar Orbiter 1. In the 1960s, during the Cold War, the U.S. and Soviet Union turned their attention to the moon. The question was who could place a man on the moon and return him safely to Earth first. Obtaining the necessary data on the moon to risk sending a person there was crucial. The U.S. and the Soviet Union chose unmanned spacecraft to obtain the necessary information. You may recall the Ranger program covered in episodes 32, 43, and 59, and the Luna or Lunar program covered in episodes 15, 18, and 70. Today, we cover 3 unmanned probes sent to the moon in 1966. Let's begin with the Soviet Luna 10, or if you prefer, Lunik 10. After the successful semi-soft landing of Luna 9, the Soviets chose a different mission for Luna 10. The primary objectives were to achieve the first lunar orbit, gain experience in orbital parameters, presumably as a precursor to an astronaut orbital mission, and study the lunar environment. The launch was timed so that the spacecraft would come around on its first orbit just as the 23rd Congress of the Communist Party of the Soviet Union was convening for its morning session. Luna 10 was similar in appearance to Lunas 4 through 9. It was designated a YE-6S spacecraft, consisting of a YE-6 bus with a fuel mass of about 1,350 kilograms, attached to a cylindrical, pressurized 240 kilogram lunar orbital module. The module was taken from the Cosmos Earth Orbiting Series. It was 1.5 meters tall and 75 centimeters in diameter at the base. The main propulsion system for lunar orbit insertion were on the bus, and the science payload was carried on the orbital module. The payload comprised 7 instruments, a gamma-ray spectrometer, a triaxial magnetometer, a piezoelectric micrometeorite detector, gas discharge counters, devices for measuring infrared emissions from the moon, low-energy X-ray detectors, and a bank of charged particle detectors. Additionally, the radio system was used for gravitational and radio occultation, which is the study of the passage of one celestial body in front of the other. Luna 10 was battery-powered, and communications were via 183 MHz and 922 MHz antennas. The first attempt to launch Luna 10 towards the moon on March 1, 1966 failed. It never left Earth orbit, so the Soviets renamed it Cosmos 111. The second Luna 10 attempt was launched on March 31, 1966 at 10:48 Universal Time. It was injected into a 200 by 250 kilometer, 52-degree Earth orbit and launched towards the moon from its Earth orbiting platform. Following a mid-course correction on April 1st, Luna 10 turned around at a distance of 8,000 kilometers from the Moon and fired its rockets. Slowing by 0.64 kilometers per second, it entered lunar orbit at 1844 Universal Time on April 3, 1966, and separated from the bus 20 seconds later. The initial orbit was 349 by 1,015 kilometers, with a period of 2 hours and 58 minutes and an inclination of 71.9 degrees. It completed its first orbit on April 4th. The data returned showed a weak to non-existent magnetic field, cosmic radiation of 5 particles per centimeter squared per second, 198 micrometeorite impacts, no discernible atmosphere, and a highly distorted gravity field, suggesting the Moon had a non-uniform mass distribution. The gamma-ray spectrometer gave compositional information on the Moon's surface, showing it to be similar to terrestrial basalt. Luna 10 operated for 56 days, covering 460 lunar orbits and 219 active data transmissions before the batteries were depleted and the radio signals were discontinued on May 30th, 1966. The orbit at that time was 378 by 985 kilometers with an inclination of 72.2 degrees. At the Communist Party Congress, the song Internationale was played over loudspeakers for the assembled 5,000 delegates on the morning of April 4th, ostensibly broadcast live from Luna 10 as it rounded the Moon. In fact, it was revealed 30 years later that it was a recording from Luna 10 from the previous night. The recording was used because the controllers did not trust a live broadcast, and because in a session earlier that morning it was discovered that a note was missing in the transmission from the solid-state oscillators programmed to reproduce the notes of the song. In conclusion, on April 4, 1966, Luna 10 became the first spacecraft to go into orbit around the Moon and the first human-made object to orbit any celestial body beyond the Earth. Yet another Soviet space first. Now let's move on to see what the U.S. was doing with their lunar probes in 1966. We will begin with Surveyor. The primary objectives of the Surveyor program, which was a series of 7 robotic lunar soft landing flights, was to support the coming crewed Apollo landings by 1. Developing and validating the technology for landing softly on the Moon. 2. Providing data on the capability of the Apollo design with conditions encountered on the lunar surface. And 3. Adding to the scientific knowledge of the Moon. The specific primary objectives for the mission were to 1. Demonstrate the ability of the Surveyor spacecraft to perform successful mid-course and terminal maneuvers and to achieve a soft landing on the Moon. 2. Demonstrate the capability of the Surveyor communications system and deep space network to maintain communications with the spacecraft during its flight and after a soft landing. And 3. Demonstrate the capability of the Atlas Centaur launch vehicle to inject the Surveyor spacecraft on a lunar intercept trajectory. Secondary objectives were to obtain engineering data on the spacecraft subsystems used during cruise, descent, and after landing. Tertiary objectives were to obtain post-landing TV pictures of the spacecraft's footpad, the surface material immediately surrounding it, and the lunar topology, and to obtain data on radar reflectivity and bearing strength of the lunar surface and on spacecraft temperatures. All in all, a pretty ambitious set of objectives. The basic Surveyor spacecraft structure consisted of a tripod of thin-walled aluminum tubing and interconnecting braces providing mounting surfaces and attachments for the power, communications, propulsion, flight control, and payload systems. A central mass extended from 1 meter above the apex of the tripod. 3 hinged landing legs were attached to the lower corners of the structure. The legs held shock absorbers, crushable honeycomb aluminum blocks, and the deployment locking mechanism, and terminated in foot pads with crushable bottoms. The 3 foot pads extended about 4.3 meters from the center of the Surveyor. The spacecraft was about 3 meters tall, the legs folded to fit into a nose shroud for launch. A .855 square meter array of 792 solar cells was mounted on a positioner on top of the mast and generated up to 85 watts of power, which was stored in a rechargeable silver-zinc batteries. Communications were achieved via a mobile large planar array high-gain antenna mounted near the top of the central mast to transmit television images, 2 omnidirectional conical antennas mounted on the ends of the folding booms for uplink and downlink, 2 receivers, and 2 transmitters. Thermal control was achieved by a combination of white paint, high IR emittance thermal finish polished aluminum underside, 2 thermal controlled compartments equipped with super insulating blankets, conductive heat paths, thermal switches, and small electric heaters were mounted on the spacecraft structure. The communication and power system compartment was held at 5 to 50 degrees C. The command and signal processing components compartment was held between -20 and 50 degrees C. The TV survey camera was mounted near the top of the tripod, and strain gauges, temperature sensors, and other engineering instruments were incorporated throughout the spacecraft. The photometric targets was mounted near the end of the landing leg, and another on a short boom extending from the bottom of the structure. Other payload packages, which differed from mission to mission, were mounted on various parts of the structure depending upon their function. A sun sensor, Canopus tracker, and rate gyros on 3 axes provided attitude information. Propulsion and attitude control were provided by nitrogen attitude control jets during the cruise phases. During the powered phases, including landing, 3 throttleable Veneer rocket engines were used, and during terminal descent, a solid propellant retro rocket was used. The retro rocket was a spherical steel case mounted in the bottom center of the spacecraft. Each thrust chamber of the Veneer engines could produce between 130 newtons to 460 newtons of thrust, and one engine could swivel for roll control. The fuel was stored in spherical tanks mounted to the tripod structure. For the landing sequence, an attitude marking radar initiated the firing of the main retro rocket for primary braking. After firing was complete, the retro rocket and radar were jettisoned, and the Doppler and altitude radars were activated. These provided information to the autopilot, which controlled the Veneer propulsion system to touchdown. Strangely enough, no instrumentation was carried specifically for scientific experiments, but considerable scientific information was obtained. Surveyor 1 carried 2 television cameras, one mounted on the bottom of the frame for approach photography, which was not used, and the survey television camera. Over 100 engineering sensors were on board. Surveyor had a mass of 995 kilograms at launch and 294 kilograms at landing. On May 30th, 1966, at 9:41 Eastern Time, Surveyor 1 was launched on an Atlas Centaur from Launch Complex 36A at the Cape. The trajectory was set for a lunar impact. Here's the clip.
-5, 4, 3, 2, 1. We have ignition. We have liftoff. Liftoff at 41 minutes past the hour. Charts are starting here at the Mission Control Center. The roll program is in and the pitch program is in as we switch to a flight azimuth of 102 degrees. Our charts are right on normal here during the early phases of the flight.
After a mid-course correction on May 31st, the spacecraft reached the Moon about 63 hours after launch. At an altitude of 75.3 kilometers and a velocity of 2,612 meters per second, the main retro rocket, signaled by the altitude marking radar, ignited for 40-second burn and was jettisoned at an altitude of roughly 11 kilometers after having slowed the spacecraft to 110 meters per second. Descent continued with the Veneer engines under control of the altimeter and Doppler radars. Engines were turned off at a height of 3.4 meters above the lunar surface, and the spacecraft fell freely from that height. Surveyor 1 landed on the lunar surface on June 2, 1966 at 1:17 a.m. at a speed of about 3 meters per second. The landing site was on a flat area inside a 100-kilometer crater north of Flamsteed Crater in southwest Oceanus Procellarum. Here's the clip.
This animation shows how Surveyor 1 looked as it came in for a soft landing on the Moon. The date, June 2nd. As evidenced by these photos, a spacecraft can land on the lunar surface, and probably a man can walk on it. Some of the terrain is very similar to our soil. A man would leave footprints as he would in sand. Many rocks dot the moonscape. Future flights will photograph other possible manned landing areas and carry instruments to measure surface hardness, information needed before men land there.
Surveyor 1's first hour on the Moon was spent performing engineering tests. Photography sessions were then initiated throughout the remainder of the lunar day. The television system transmitted pictures of the spacecraft's footpad and surrounding lunar terrain and surface materials. Some 10,338 photos were returned prior to nightfall on June 14th. The spacecraft also acquired data on the radar reflectivity of the lunar surface, bearing strength of the lunar surface, and spacecraft temperatures for use in analysis of the lunar surface temperatures. Surveyor 1 was able to withstand the first lunar night and near high noon on its second lunar day, July 7th. Photos again were returned. On July 13th, at 2:30 a.m. Eastern Time, after a total of 11,240 pictures had been transmitted, Surveyor 1's mission was terminated due to a dramatic drop in battery voltage just after sunset. Engineering interrogations continued until January 7, 1967. All mission objectives were accomplished. In conclusion, Surveyor 1 was the first spacecraft launched in the Surveyor program, and it performed the first soft landing on the Moon by the United States. The mission was considered a complete success and demonstrated the technology necessary to achieve landing and operations on the lunar surface. In total, the Surveyor program involved building and launching 7 Surveyor spacecraft to the Moon at a cost of $469 million. Here's the NASA clip.
The success of Surveyor 1 is almost legendary. It soft landed on the Moon in the Ocean of Storms on the 2nd of June, 1966. and returned over 11,000 photographs of soil, rocks, and topography. It showed the color of the moon's surface and recorded the changing temperatures for more than 3 lunar days and nights. Ranger and Surveyor are part of a carefully planned series of missions designed to photograph and explore the moon's surface and to find the best landing sites for Project Apollo.
Now we will move on to the final unmanned spacecraft I want to cover in this episode, Lunar Orbiter 1. The Lunar Orbiter 1 spacecraft was designed primarily to photograph smooth areas of the lunar surface for selection and verification of safe landing sites for the Surveyor and Apollo missions. It was equipped to collect selenodetic data which applies to mapping the moon's size, shape, surface topology, and its gravitational and magnetic fields. It was also equipped to collect radiation intensity and micrometeoroid impact data. The main bus of the lunar orbiter had the general shape of a truncated cone. It was 1.65 meters tall and 1.5 meters in diameter at the base. The spacecraft was comprised of 3 decks supported by trusses and an arch. The equipment deck at the base of the craft held the battery, transponder, flight programmer, inertial reference unit, Canopus star tracker, command decoder, multiplex encoder, amplifier, and the photographic system. 4 solar panels were mounted to extend out from the deck with a total span across of 3.7 meters. Also extending out from the base of the spacecraft were a high-gain antenna on a 1.3 meter boom and a low-gain antenna on a 2.1 meter boom. Above the equipment deck, the middle deck held the velocity control engine, propellant, oxidizer, and pressurization tanks, sun sensors, and micrometeoroid detectors. The third deck consisted of a heat shield to protect the spacecraft from the firing of the velocity control engine. The nozzle of the engine protruded through the center of the shield. 4 attitude control thrusters were mounted on the perimeter of the top deck. 375 watts of power was provided by the 4 solar arrays containing 10,856 solar cells, which would directly run the spacecraft and also charge the 12 amp-hour nickel-cadmium battery. The batteries were used briefly during periods of occultation when no solar power was available. Propulsion for major maneuvers was provided by the gimbaled velocity control engine, a hypergolic 100-pound thrust Marquardt rocket motor. 3 axes stabilization and attitude control were provided by 4 1-pound nitrogen gas jets. Navigational data was provided by 5 sun sensors, a Canopus star sensor, and the inertial reference unit equipped with internal gyros. Communications were via a 10-watt transmitter and the directional 1-meter-high antenna for transmission of photographs, and a 0.5-watt transmitter and omnidirectional low-gain antenna for other communications. Both antennas operate in the S-band at 2.295 GHz. Thermal control was maintained by a multi-layer aluminized mylar and dacron thermal blanket which enshrouded the main bus. Special paint, insulation, and small heaters were used as well. Here's a NASA clip describing the lunar orbiter.
Lunar Orbiter is best described as an orbiting photographic laboratory. Unlike earlier photo missions which used a television type of camera, Orbiter takes its pictures on 70mm film. It develops the pictures and stores them until it is time to send them back to Earth. The whole craft is similar to a 4-leaf clover with a thick stem. The leaves contain the solar cells that provide power for the various systems on board. And the stem contains the 2 lenses, the film processing unit the picture transmission equipment, and the various scientific instruments, such as micrometeorite detectors and radiation counters. At the heart of Lunar Orbiter is the photosystem. Pictures are taken simultaneously with the two lenses, one close-up and one wide angle. A device called a velocity height sensor determines the speed of the spacecraft relative to the moon's surface, normally over 4,000 miles an hour. As an exposure is being made, it moves the film proportionately to avoid blurring the image. The film then moves into the processor, where it is rolled into contact with a bimat web, a material that has been soaked in a solution that develops and fixes the image. It is then separated from the web and dried. The method of getting the picture from the moon to Earth is one of its most exacting tasks. The film is scanned by a light beam 1/20th as thick as a human hair. As the beam passes through the film, its intensity varies as the density of the image varies, and this variation is detected by a photoelectric cell. This converts the light into electronic signals which are transmitted to Earth. They are then converted back to light, and the picture is reconstructed. Each frame, consisting of one close-up and one wide-angle photo, requires 45 minutes of transmission.
On August 10, 1966, Lunar Orbiter 1 was launched by an Atlas SLV-3 and an Agena D. Here's the clip.
A typical Lunar Orbiter mission begins, after all of the checkout procedures have been completed, with the orbiter perched atop an Atlas Agena launch vehicle at Cape Kennedy, protected by a magnesium shroud.
2, 1, 0.
The Atlas ignites, pushing the spacecraft through the thicker atmosphere. After a little more than 5 minutes, the Atlas engines shut down, and the stage separates and falls away, followed in a few seconds by the shroud. The Agena's second stage engine ignites long enough to place the combination into a parking orbit.
At 1921 Universal Time, the Lunar Orbiter was inserted into an Earth parking orbit. At 2004 Universal Time, the spacecraft was placed into a lunar trajectory. The Lunar Orbiter experienced a temporary failure of the Canopus star tracker, probably due to stray sunlight and overheating during its cruise to the moon. The star tracker problem was resolved by navigating using the moon as a reference, and the overheating was abated by orienting the spacecraft 36 degrees off sun to lower the temperature. 92 hours after launch, Lunar Orbiter 1 reached the moon and was injected into an elliptical lunar orbit. Here's the clip.
When they arrive at an acceptable position from which to head for the moon, the Agena's engines ignite for the second time, boosting the spacecraft out of its parking orbit. The Agena then separates, sending the spacecraft on its way to the moon. Then, on command from Earth, the Lunar Orbiter begins to assume its familiar shape. The solar panels fold out to pick up the sunlight, and the radio antennas are extended for communications with Earth. A sensor locks onto the sun, aiming the panels so they can begin transforming the sun's energy into needed electricity. Several hours later, another sensor, designed to respond to Canopus, the brightest star in the southern sky, picks it out and locks on it. These two lock-ons are necessary so that ground controllers know the position of the spacecraft for future maneuvers. For the next several hours, the course of the spacecraft is carefully plotted against the known path of the moon. A decision can be made that a mid-course correction is required for perfect aiming. This is accomplished by rolling and pitching the spacecraft to the desired attitude and firing the velocity control engine a given period of time, either to speed it up or slow it down relative to the speed and direction of the moon itself.
Lunar Orbiter 1's initial orbit was 189 kilometers by 1,867 kilometers, and it had a period of 3 hours and 37 minutes. The spacecraft acquired photographic data from August 18th to the 29th in 1966. and readout occurred through September 14, 1966. A total of 42 high-resolution and 187 medium-resolution frames were taken and transmitted to Earth, covering over 5 million square kilometers of the Moon's surface. This accomplished about 75% of the intended mission, although a number of the early high-res photos showed severe smearing. Lunar Orbiter 1 also took the first 2 pictures of the Earth ever from the distance of the Moon. Accurate data was acquired from all other experiments throughout the mission. Orbit tracking showed a slight pear shape to the Moon based on the gravity field, and no micrometeorite impacts were detected. On October 29, 1966, Lunar Orbiter 1 was deorbited, and it impacted the lunar surface on the Moon's far side on its 577th orbit. The early end to the expected one-year mission was due to the small amount of remaining attitude control gas and other deteriorating conditions. There was also a concern about Lunar Orbiter 1 creating a communications hazard with Lunar Orbiter 2. In total, the Lunar Orbiter program consisted of 5 lunar orbiters, which returned photography of 99% of the surface of the Moon, both near and far side, with a resolution down to 1 meter. Altogether, the lunar orbiters returned 2,180 high-resolution and 882 medium-resolution frames. The micrometeoroid experiment recorded 22 impacts, showing the average micrometeoroid flux near the Moon was about 2 orders of magnitude greater than in interplanetary space, but slightly less than the near-Earth environment. The radiation experiments confirmed that the design of Apollo hardware would protect the astronauts from average and greater than average short-term exposure to solar particle events. The use of lunar orbiters for tracking to evaluate the Manned Spaceflight Network tracking stations and Apollo Orbit Determination Program was successful, with 3 lunar orbiters, 2, 3, and 5 being tracked simultaneously from August to October 1967. Eventually, all of the lunar orbiters were commanded to crash on the Moon before their attitude control gas ran out, so they would not present navigational or communications hazard to later Apollo flights. The total cost of the Lunar Orbiter program was $163 million. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.